my name is Li-Fu Wang, and today we're going to go through an Abaqus tutorial on 2D heat transfer problem. We're going to comparing steady state analysis versus transient problem. Before we start the actual tutorial, let's go through the problem statement first. Assuming you have a thick steel shell whose conductivity is 48 with specific heat 470 joules and density equals to 7850. The dimensions of the thick steels is 0.6 in width and 1 meters in height. We have an essential boundary condition with the initial temperature equals to 100 Celsius. The left wall is insulated, and the top wall and right wall has a contact with the ice water whose convection coefficient is 750, and the ambient temperature is 0 degrees Celsius. Before we actually go to the GUI of the Abaqus, let's talk about the difference in steady state and transient problem. Both steady state and transient problem share the same heat transfer governing equations, which is the heat conduction and the heat convection. The only difference between steady state problem and transient problem is their assumption of the heat of the transient state heat. For steady state, we already assume the inlet energy equals to the outlet energy, so there's no temperature change in between. While for transient problem, we assume at each time we have a inflow energy and outflow energy difference, and this difference will result in a temperature change, and is related to the density and the specific heat also. Now let's go through the Abaqus. So first we create a part. We kind of want the left corner to be the origin of our system. So we create a steel shell, and we make a 2D planar deformable shell. Maximum size, we use our maximum dimension. And your origin, which is left corner of your rectangle, 0, 0. And the right is your dimension is 0.61. Done. Here is your plate. Now in property, we assign the steel property. Notice for steady state problem, you actually don't need, as your governing equation doesn't have density and specific heat, what you only need is the conductivity. So thermal conductivity, and the value is 48. And we create a section which is solid homogeneous. We want it to be plane strain, 1 unit dimension, okay. And then we don't want to create sets and assign the section to our geometry. Now we can go to assembly to create an instance. Create instance, mesh on instance, apply. Before we actually move to the next step, we want to kind of find a point to probe the value and later to show the difference between the steady state problem and the transient problem. What we do is we do a datum plane first, which is an extension of XZ plane with the offset 0.2. So we want the probe point to be 0.2 and on the right of your panel. So we cut the geometry. Sorry, this is a 2D geometry. Cut the geometry by the datum plane, create partition. Now you can see the partition. It's partitioned into two parts. We also create a data point which is 0.6, and here we do 0.2. And this give you the probe point. Later, this will be our time to our point to show the time history. Now we can move to the step. To the step create, we need the steady state analysis. Definitely, we need a heat transfer and change it to steady state. We haven't assigned the load, so that's fine. For steady state, the time period doesn't make too much difference. And all these things are, you can keep it the same, but I want to make it to 0.1 because steady state, normally you one step is not enough for you to actually reach steady state. So there are several intermediate steps, but those are not physics. Those are like mathematical skills. I want to show you those mathematical skills to kind of compare to the transient problem, see what's the difference. That's why I changed to 0.1. Okay, check again. Heat transfer steady state. Cool. Now we assign the history output. We call it. We can assign that later. After we actually make the node, we can assign that. Now we can make interaction first. When you have interaction, we only have here and here is contact with the ice water. So let's say convection. Definitely during the analysis and surface film condition. Select the top edge and the right edge. Notice that you have two right edge. Done. Film coefficient is 750. And the temperature is 10. Sorry, temperature is 0. When you see those yellow dots, it's signed correctly. And then before we make the load, actually we can make the load now. The only load we have is net essential boundary condition at the base, which is temperature equals to 100. So we can create the base temperature or directly base T. At the analysis temperature continue and select the bottom edge and then magnitude 100. Now we go to mesh. This part you need to be careful. Select the entire body. In the element type, you need to select the heat transfer element. Make sure your element is DC2, D4, which is a 4-node linear element for heat transfer. Okay. And make sure this is done correctly. DC to D4. Okay. So now I like to make the mesh type, change it to structure, make it more uniform. When it turns to green, it means it's okay. Mesh size, the seed global size 0.08 is too large. Make it 0.01, especially for transient problem. And assign match the instant, you will get this one. Now we need to create a set, because what we haven't said is, other than this line, what's the initial temperature for rest of the entire body? It should be the same as the environment temperature. Let's call it initial temperature. So it should be every point except the point we just assigned for the temperature. Make sure there's no point here. Okay, done. Go back to XY. We can create another set, which is our probe set. Our probe set is here. Select the correct point and done. Once we have the set, let's go back to step first. We need to create the history output. Let's call it probe value. We don't need a whole model, we just need a probe set, and what we only need is under thermal only the nodal temperature. And then in the load, we assign the predefined value. Let's say initial temperature. Others temperature, yes. And because we already have the set, select the initial temperature set and define it as 0. And you can check again, make sure everything good, like still 848, especially the step steady state, and everything looks okay to me. Now we can move on to job. Create your job. Steady state analysis. So I would like to use the parallel computing. To see your parallel computing, you can go to performance. I have 12 logical processor here, so probably I will use 10 of that, and GPU computing as well. And now submit. Can turn on the monitor. Sorry, I didn't run this one. It says you need to see the status as submitted. Now you can turn on your monitor. You can check your warnings and arrows here. Normally it will show some message. Sixth step, and it reaches the time 1. That means it's complete. Yes, it's complete. Now we can see the result now. Use this one and change the value to temperature, and you can see the steady state temperature. But remember, we have also include the intermediate steps. So that means we can kind of play the animation. It's too fast. Use this to control your animation speed. So this is just mathematical intermediate step. It's not your physical. How your real physics look like. And okay, let's stop. Besides, we have also the tools, XY data, create, history output. As we have this one, plot, you can see that it's a linear line all the way to this value. And so it's not really a transient problem. It's more like 0 all the way connect to this point, which is your last value for that. And that's it for our steady state analysis. Then we move on to our transient problem. For transient problem, let's close this one. For transient problem, first of all, unlike steady state problem, you need to add more material property here. First, definitely is density, which is 7850. And then we need a specific heat, which is 470 here. And everything, you can just keep it the same. And then the step edited, we can suppress this step and create a new step from that called transient analysis. Again, heat transfer and transient time period, because we don't know how long it's gonna take to reach a steady state. Let's put like 20,000 seconds. Initial step, again, let's move it 0.1. Minimum step 1e minus 4. And ending step, that means if you want it to be converged faster, you can put this one as a very small number, 1e minus 4. If your temperature changes less than this value, then it will stop. Then maximum allowable temperature change. Let's do 1 here, because you don't want your transient problem, each step your temperature changes too much. And increment, let's do 150. It may not run correctly, but let's see. So transient problem, heat transfer, good. And now the interaction. You can see that the interaction is suppressed now because it's related to your analysis step. Create a new step, which is convection here. Transient analysis, again, surface film condition. It complains about that, so we can delete this one and recreate another one of convection. So surface film. And assign this and this age, and also this age. And sorry, I didn't assign that. Convection. This age, and this age. Done. Now the film is 750. Temperature 0. Okay, so it's already set. And now you go to load. This one, because we assign it a transient, is also changed. So we delete this one, create the base temperature, and done. 100. And also your field, initial field, let's see the manager. This one, because it's created in the initial step, so it's still okay. So everything seems okay now. We just create a new job called Transient Analysis. Again, we want 10 processor here. And submit. Oh, this field output is because we changed the thing, so the field output is not valid. We can queue this one first, and then go back to change our field output. Create the field output on the transient analysis, and hold this turn. And this time we just need the temperature. We doesn't need other items. Similarly, for history output, create probe value. Two. So set and the probe set thermal only temperature. Yeah. And we can delete the previous one. And load. Everything looks okay. Now go back and submit this again. While working, you can always open your monitor to see what's happened. It reports an error. That arrow means like you have a file aborted, but now it's okay. It went through smoothly. You can see the time recorded here is like 7:42 and something. And this 150 increment is already stopped and it reports an arrow. That arrow means the step hasn't finished. That means the transient problem haven't go to the convergence thing. That means our step is not enough. So we can go back to the step at the transient problem and change this one to 400 because it seems like it's pretty quick, just in case. And then make it just leave it as 1. So let's go to the job. If you feel like it's too slow, you can change that to 2 the maximum allowable temperature changed to 2 or some other things. Let's submit the job again. We haven't had the results. Open the monitor to see how your analysis is working. Okay, your analysis went through smoothly. And here you can see the time, total time. Now we go to 17 seconds. And the step time is increasing. Total time now go to 113, 292. That means it needs relatively a long time to reach convergence. But now it's already 1,000, 4,000. Okay, it reaches our maximum analysis time. I hope it's already convergent, but let's see. If you see the result, you can see the temperature distribution. It looks kind of like our static analysis. That means it may works. Now we just need to play the animation. So your animation shows similar things as your steady state analysis, but notice that they're totally different. One is real physics, the other is just mathematical intersteps. And finally, we can create our data history and select the probe point. You can see your temperature. The temperature converged to almost the same value as we have in steady state, but this time it has a clear transient behavior. Previously, steady state is just a linear line. It means it just have the initial state and the ending state. This shows you the process, how it changed. That's the main difference between steady state and transient analysis. Okay, so that is all our work on steady state 2D heat transfer problem, comparing steady states and transient problem. So hope that you will learn something, and thanks for listening to this video.